So, could you sort out the room where we would have the lab class, which is day after tomorrow, isn't it? From 3
Uh,
to 6. Yeah.
Excuse me, sir.
Yeah.
Uh, Sir, I'm yet to talk with the LHC office people. I'll talk
Okay.
with them today and I'll let you know, sir. Let you and
Okay.
Adil know.
Fine. 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 That's fine.
Okay, sir.
All right. So, in the last three lectures, what we have been doing, we have been understanding some basic introduction around structural geology. Okay. So today, formally, we will start one of the most important topic on structural geology. It is the concept of strain and deformation. Okay. So what we are going to understand in next 3 or 4 lectures is around the overview of deformation, displacement, velocity vectors, particle paths. We're going to talk about homogeneous and heterogeneous deformation. We are going to look at strain both in one dimension, two dimension, and later on in 3 dimension too. We're going to describe strain with the help of something called strain ellipse. And in case of strain in 3D, strain ellipsoid. And then we are going to discuss about something called coaxial and non-coaxial deformation. Coaxial deformation is also called pure shear, and non-coaxial deformation is called simple shear. Okay, so as the time comes, we will discuss what exactly are they. So, what is deformation? So, deformation is, as it is defined, it's very simple: a change in form and shape of an object. Okay, change in form or shape of an object, and that typically happens because of the application of force, or in our particular case, we will say due to the application of stress. Okay, due to the application of stress. Okay, so a change in form or shape due to the application of stress. So when we discuss about stresses, we are mostly looking at the dynamic aspect, because that's related to the forces. And when we look at strain or deformation, okay, that is essentially our kinematic aspect. Okay, kinematic. So deformation is the transformation of an initial to a final geometry by means of, so from an initial geometry to a final geometry. So when we are discussing final geometry, it's geometrical modeling, we talked about it. So from initial geometry to a final geometry by means of rigid body translation, rigid body rotation, distortion, and or volume change. So these are the processes by which a particular object attains deformation. Okay, and we are going to look at all of them one by one. So deformation relates to the positions of particles before and after the deformation history. Okay? And the position of points before and after the deformation can be connected with vectors, and those vectors are called displacement vectors. Suppose there was a point A before deformation. After you apply some force, that essentially shifts to point B. Then this AB would be my displacement vector. Okay? As simple as that. Now, the actual path each particle follows during the deformation history is referred as particle path. Okay? So, what do I mean by that? So, for example, what can happen that with the initial example, A and B, we said, so this is my displacement vector. Now, A can come to B by any paths. Like, for example, it can go like this and go like that and then reach here, or it can go like this and then reach here, Okay, can go like this and reach here. Okay, so although the displacement vector is AB, the particle path could be anything. So this is essentially when we discuss about particle paths, we are actually looking into the incremental deformation, right? Incremental deformation. And when we are looking at the displacement vectors, we are actually looking at the finite deformation, right? Finite deformation. Finite deformation means this is the displacement between the initial and the final, and the particle paths essentially, or the incremental deformation refers to all the intermediate paths it does take to reach from one A to B. Okay, I hope this point is clear to you. Now let us look at a rigid body rotation, rigid body translation. It's very simple. Let's look at the first object. So moves every particle in the rock mass in the same direction and the same distance. The displacement field consists of parallel vectors of equal length. Okay, I think this is, I don't have to explain it twice. So you can see here I have a like a uh, like a block. Okay, and then I have put some sort of marker, like a circular marker into it, and this is before deformation at initial position T1, and then I give it some translation. It All the particles actually move in the same direction with the equal amount. Okay, so I can typically describe the displacement vector, the displacement field, with these blue arrows, and I can also, the particle paths will be parallel to it. Okay, particle paths will follow the displacement vector. Okay, now it doesn't have to be essentially along x-axis; it can be along any axis. Say, for example, here it is like following 45-degree angle with respect to the displacement vector is following around 45-degree angle with respect to the with the x-axis, right? So this is my position A, which is translated to position B, and these will be my corresponding displacement vectors and particle. Okay, I hope this is clear to you. So now the next type of strain we are looking at is rigid body rotation. So involves uniform physical rotation of rock volume relative to an external coordinate system. Okay, so this is important, that there must be an external coordinate system with respect to my body will rotate uniformly along a rotation axis. Okay, which is in this particular case is actually designated with a plus sign. Okay? Now this is my initial position of the object that we are considering, and then I have given it like a clockwise or anti-clockwise rotation. In this particular case, I have given it a clockwise rotation, and this is my final position. Of course, then this is my axis of rotation, and then my displacement vectors will be parallel to the tangents, right? As so would my particle paths be. Of course, the particle paths is curved, as you can see, but the displacement vectors are straight. Okay, so you can see here that my displacement vector and my particle path is, although they are in the same direction, they are little bit deviating, right? In case of translation, they were parallel, but in case of rotation, we can observe that the displacement vectors are, of course, straight lines, but the particle paths has to be of curved lines, right? So we can see here in an example, the first example is where the axis of rotation is at the center of the object, and in the second example, the axis of rotation is at the corner of the object, and the corresponding displacement vectors and particle paths. Okay, so it's important in any while we define any sort of strain, right, or any sort of deformation, we need to essentially describe it in terms of the displacement field or the displacement vector and in terms of the particle path. We need to see whether they're parallel to each other or whether there is some sort of discrepancies in between. Okay. Now, of course, you can think of the rotation of a or the movement of a particular plate, you know, and then what we can see here, for example, the movement of India from 70 million years before present to present. I mean, 0 million years before present, and this is how Indian plate essentially moved. We generally observe a northeastern translation, and then it actually was more like a north-south translation of. But then this depends on the scale. You can see that in this particular scale, of course, we are looking like a translational movement. But we all know that on a particular, these plates do not really have translational movement. They are generally the type of movement that these plates actually have are rotational. And we have defined Euler's pole, if you remember. Yeah. We defined Euler's pole is the pole around which such plates actually move. So it depends also on the scale, and the reference frame. In the reference frame of India, if we are just looking at it, it looks like translation in both directions. But then if you are like zooming out, then you can observe that it's nothing but the rotation along around the Euler's pole. Right? So this is an example of a rigid body rotation as well. So now there is the next category. We call it distortion, and distortion is typically also called strain. So any non-rigid change in shape, okay, without in change in volume is referred to constant volume strain. Okay? So any non-rigid, I mean, it's a non-rigid sort of deformation. So here there is no like a rigid body rotation or a rigid body translation, but there could be cases where the volume is kept constant. There are cases where volume is actually changed. We will discuss later on when the volume changes how it looks like. But for the time being, let us refer to something where we are looking at a constant volume strain. Okay, the particles in the rock have changed positions relative to the others involving either or both translation and rotation. So we can see here the first one. This is my initial shape of the object. Of course, the object is no more a square. Okay, so as if this part of the object is kind of kept stationary, and like a shear has been applied, and the body is deformed. Now, what is important to remember that we are looking at in two dimension. Of course, here we are talking about constant volume strain, so it must be translated in three dimension. But in here, because it is we are talking about constant volume strain in 2D, it should be constant area strain. So the area, whatever was here, before deformation and after deformation, if you calculate the area, it should be the same, right? So that is what my constant area strain in two dimension or constant volume strain in three dimension. Yeah. So this is the corresponding displacement path. What I am observing, of course, that something which is at the outer arc of the object has the maximum displacement, and something which is in middle of the object has almost no displacement. And from the somewhere in the halfway where there is no displacement, the displacement vectors are actually oppositely directed. Okay, so here if the displacement vector is towards east, here the displacement vector is towards west, right? So here it is west towards east. Okay, and somewhere in between I have zero displacement, right? And that is essentially followed by the particle path as well. But here you can of course observe that the particle path and the displacement vectors are kind of parallel to each other. Okay, and the second kind of deformation, constant area strain in two dimension or constant volume strain in three dimension. What I'm essentially observing, I'm squeezing my block from one direction. So what is happening, I am shortening in this direction. and I'm extending of the object in the perpendicular direction. So this is my final shape of the body. Okay, and this would be my, of course, my if I do a good job, what I will observe that this is my point A. That point has come here, A dashed. So my displacement vector is like this. Okay, like you are observing here. Okay. Similarly, here, if this is B and this is B dash, then my displacement vector is oppositely directed, right? Here. Okay. And then, but the particle path, of course, is hyperbolic. Okay. The particle path will not be straight line, they are hyperbolic. Okay. And this is how they look like. Okay. I hope you can appreciate how this deformation is going on. Okay. So these are the two type of volumetric constant volume strain that we are talking about. By the way, this type of constant volume strain, okay, and we will define it better later on. This type of constant volume strain is called pure shear, and this is what we call as simple shear. We will see them in bit more details later on. For the time being, just to give you a heads up. Now, the next type of strain is called dilation, distortion, okay, or volumetric strain. So what I am observing, there are two ends to it. The first one, this is my initial object, of course, and the final is, it has just increased in volume. The shape has not changed as much, but then it has only increased in volume. And the second one is it has shrunk in volume, okay, or shrunk in area into dimension, of course. And these will be my corresponding velocity vectors and particle path. Okay, so if you start, I mean, these things you don't have to remember. If you start, um, you know. Take a small block in your PowerPoint, okay, and then squeeze it, or extend it, and see how each point actually translates. You will be able to form these displacement vectors and corresponding particle paths. I hope this is clear to you. Okay, and this sort of strain we call it as volumetric strain. Okay, dilation, positive or negative dilation. Positive dilation means increase in volume, and negative dilation means reduction in volume. Okay. Now, often such displacement is studied with something called strain marker. Okay. Strain marker means, I'll give you an example that then you will be able to understand what strain markers are. So the strain marker that I am going to discuss in this particular case is on an experiment, on an analog experiment. But of course, there are such strain markers present in nature too. Okay, so for the sake of simplicity, I am explaining it in an experiment. But then we will observe that plenty of such strain markers are also present in nature. Okay, so what I am observing here, what I am doing in this particular experiment, it's a very primitive sort of experiment, but you can do it at home as well. Okay, so what I'm doing is I have a clay block. These sort of clays are available, in the market, and I recommend you buy some for yourself. This will be fun. We do experiments with such clays in our lab as well a lot, but then you can buy them in small quantities and play with your, play at home. And the concepts of structural geology will be very, very clear if you have something to deform at your hand. Okay? So what is it? This is like a three-dimensional simple uh, block of a clay. And then what you have done here, in the middle you have created a slit. Just you have taken a ruler or a scale, and then you have inserted it and kind of made a slit inside, as if you have made a slip plane inside. Okay, and then what I have done, what is put some like grid lines, like some north south lines and some east west lines, like making some small squares here, yeah, like it has been shown in this with these blue lines on this particular figure. Okay? So this is my initial uh, um, experimental setup, and then I deform it with pure shear deformation. Okay? So what I'm doing, I'm giving some sort of pressure from this side, okay, and I'm allowing the material to expand on the other side. Okay, and the third dimension, which is like the perpendicular to the screen, that part I have kind of kept some sort of resistance, so that it doesn't flow in that direction. It only flows. So I'm flowing it. I'm giving pressure from y. I'm keeping my x direction open, and I'm keeping my z direction kind of restrained, so that there is no material flow along that direction. I hope I'm able to explain the model setup to you. Okay, and then after the deformation, after I have provided such sort of forces or stresses, what I am observing, I am observing these individual, how these individual um, blocks, or the blocks that I have drawn, have actually deformed or got reshaped. Okay, so I can very well see, very close to the slit, some sort of deformation happening, some sort of slip happening, all sorts of things. Can you observe them? Beautifully, beautifully done. Okay. Now what I can do, I can essentially say that all these intersection points of the grids, of my initial grids, are my individual points or my particles. Okay, are my particles. And then, so this is my initial state, and then I can observe how these individual uh, you know points have moved after my deformation. Okay? And which direction it has moved, how much it has moved, I can simply measure them with a piece of scale, or I can do that with the help of the image analysis software as well. Okay? I can do that with the help of an image analysis software. What I have to understand for each of these particle A, B, C, D, E, F. Okay, okay. What is the direction it has moved? Okay, and how much it has moved, and then I can create a picture something like this, where each individual arrow actually denotes the direction of the displacement field, and the length of that particular arrow denotes the magnitude of the displacement field. Okay? How much that point has moved and in which direction that point has moved. And we can create this beautiful strain diagram, out of this experiment. Okay? Of course, this is a very primitive experiment, but the philosophy remains pretty much the same when you do numerical modeling as well as analog modeling to understand nature, to understand deformation, to understand kinematics. You need to put certain strain markers, okay, and you need to observe the deformation of the strain markers in two quantities. One is its direction of the displacement, as well as the um, magnitude of the displacement. Okay, is that clear so far, everyone? Or do you have anyone has any question? Is there any question, guys? Nirul, you are unmuted. Can you tell me if you have? Do you have a question, Nirul?
No, sir.
Okay. Anyone else? Was it clear so far? Okay. Excellent. If not, let me just continue. Okay. Now, such type of displacement vectors can be studied in nature as well. Now, this is what you observe here is the is similar to what I have been showing, in that experiment. So there are arrows, but you can see here real continents, okay, and the displacement vectors of the continents. Okay. Now, in this particular case, this is the GPS vectors and seismicity of Northwest India and Southern Tibet, keeping Indian plate fixed. The colored arrows indicate the GPS vectors derived from different sources. Okay, so you can actually install geographical positioning system, and connect it with the satellites, and that records ground motion. Okay, records ground motion. Okay, ground motion or simply the displacement vectors. What does that mean? With respect to a fixed point, with what magnitude and in what direction a particular point has moved at which that GPS station is installed. Okay, and you can see there are plenty of GPS stations now installed around the world, and you can have a very good understanding of how these plates are moving relative to each other, in which direction, as well as at what magnitude. If you observe the relative disposition of these vectors. Okay, it is pretty easily done, but fundamentally this is nothing different than the experiment that I had just described. Okay, now let's talk about something called homogeneous deformation. So we talked about homogeneous and heterogeneous, what they are, what do how would you identify them in our introductory class? But let's see, in terms of deformation, what do we call a homogeneous deformation? So if given strain may be accumulated at an infinite number of ways, whereas the deformation applied to a rock volume is identical throughout the volume, the deformation is called homogeneous deformation. So the deformation is applied to a rock volume is identical. It is the same everywhere throughout the rock volume. Okay. This is what we call homogeneous deformation. Okay. So what I'm observing here is that a few examples of homogeneous deformation. So this is my precursor rock, of course. This is my precursor. This is my precursor rock. You can see some sort of fossils present there. And these fossils right now are acting as what? Can you tell me what are these fossils acting as? These circular fossils are acting as strain markers, right? They are all my strain markers. Okay. Now you can see that in this particular case, the fossils have been deformed by pure shear deformation. Okay, the circles have kind of converted into ellipses. Okay, or it can be deformed as simple shear deformation as well. But then what I am observing that the type of deformation is same everywhere in the rock, be it pure shear, be it simple shear. What do I mean by the same sort of deform everywhere the same? Say, for example, if I calculate the aspect ratio here, and if I calculate the aspect ratio here, and calculate the aspect ratio here, calculate the aspect ratio here between the major and the minor axis, I will attain the same value. Similarly, here is my simple shear deformation. If I calculate the angle here theta, and if I calculate the angle here theta, everywhere I will found that this is the same angle theta that is going on. Okay, so here the aspect ratio would be the same, and here the angle would be the same. So that means that this particular precursor rock has been deformed either by pure shear or by simple shear, but I can observe that the same sort of deformation is consistent throughout the rock body. And this sort of deformation is called homogeneous deformation. There is a formal definition of homogeneous deformation. So for homogeneous deformation, original straight and parallel lines will be straight and parallel also after deformation. Also, identically shaped and oriented objects will also be identically shaped and oriented after the deformation. Okay, so this is how we define homogeneous deformation. In a nutshell, the deformation, whatever way it is, be pure shear, be simple shear, or any other sort of deformation that we would study later on, every at every part of the object, the deformation is the same. Now, of course, the opposite is heterogeneous deformation. That means everywhere the deformation is not the same. And these are two different examples of heterogeneous deformation, of course. You can see this is the precursor rock. And if I do a calculation of in the first picture, this is deformed. In the second picture, it is also deformed. But if I take these individual strain markers and I calculate the aspect ratio of these ellipses, I will see that it's different from one place to the other. So we will say that this is heterogeneous deformation. Now, homogeneous deformation and heterogeneous deformation does very much depend on scale. Okay. Now, if I want you to concentrate only at this part of the deformed body. Okay, so this is my precursor material, and this is after deformation. Okay, and I want you to concentrate only at this part. Here, if I go to each of these cells, I see that the deformation is similar. Okay, so if I am only concentrating at this scale, I can say this is homogeneous. But then if I am concentrating on this whole object, of course, I will say this is heterogeneous deformation. Okay, so homogeneous deformation and heterogeneous deformation also depends on scale. Okay, so something that appears homogeneous on a smaller scale might appear heterogeneous at a larger scale. Okay. Now let us try to give some what is that called? Some numericals around it. Okay, some numbers around strain. So strain in one dimension, we are looking at linear strain first. So linear strain means strain measured in one dimension. Okay, so this is the undeformed rock which has a length of 120 millimeter, 120 meter, whatever it is. Okay, and then I am extending this bit of rock, of course, by the means of forming a normal fault inside it, and I see that the final length is 130 millimeter. So that means L1 minus L0 is actually 10 meter, right? 10 meter. So that means I have so forget about the presence of the normal fault. You can simply think of a L0 length. After deformation, that becomes L1. Okay, and in this particular case, L1 minus L0 is 10 meter. Of course, in this particular case, the deformation has been accommodated by the presence of a normal fault. Okay, we can also see in nature. We will see later on that this normal fault might not be necessary always. This particular strain can be also accommodated by thinning of the strata. So what do I mean by that? Suppose I had a layer which has a length of D1, sorry, thickness of D1 and length L1, it can become L2, which is elongated than L1. And to accommodate that extra length, I can have a reduced thickness. It becomes D2. I don't necessarily need to make a normal fault. But in this particular case, you observe that the L0 becomes L1 by the accommodation of a normal fault. Here also, it's also longitudinal strain, but you can see that the individual layer thickness is kind of conserved. Here, the individual layer thickness is kind of conserved. So these are two examples by which, in one case, the linear strain is accommodated by thinning of the layer, and in the second case, it's by introducing a slip plane or introducing a fault plane. Okay. In the first case, of course, it is thinned, but in the second case, it is not thinned. It's simply introduction of a slip plane. Whatever the reason is, I mean, whatever way the strain has been accommodated, the longitudinal strain, there are some parameters which are used to define longitudinal strain. The first one is called elongation. So elongation is the ratio of the change in length to the initial length. So delta L by L0. Okay? So epsilon, elongation is denoted by epsilon. That is delta L by L0, that is the initial length. And in this particular case, it is 0.083. Then something called stretch, the ratio between the deformed and the undeformed. So that means L1 by L0. L1 is the final length, L0 is the initial length. And you can of course express that as 1 plus epsilon. In this particular case, it is 1.083. And then there is something called quadratic elongation. Quadratic elongation is nothing but the square of the stretch, and that is expressed by lambda, which is s square or 1 plus epsilon whole square. And in this particular case, it is 1.174. Okay. So elongation, stretch, or quadratic elongation, they are the parameters that are generally used to actually define linear strain. Okay. And it will depend how we are going to I mean, it depends on our purpose, but it's essentially the same thing. If you know elongation, you can calculate stretch or quadratic elongation, no problem. Okay, but that's how linear strain is generally defined. Now let's look at something called angular strain. Okay? You can see here, just by looking at the picture, it's very evident that after deformation, there is like an angular deformation. So this whole thing has kind of gone down around this rotational axis, Okay? And the angle xi is around 40 degrees. So the shear strain, okay, so the angular strain is also called shear strain, will be nothing but tan of this angle. Okay? In this particular, then tan of 40 degree become 0.84. Okay. So the next is strain in 2 dimension. In 2 dimensions, during homogeneous deformation, an imaginary circle on the surface of the deforming rock takes the shape of an ellipse. Okay? A circle. And of course, we will call this circle to be a strain marker, okay? An ideal circle which would transform into an ellipse. Okay? Now, of course, the ellipse can look like this, or the ellipse can look like this as well. It doesn't matter. It will depend whether we are looking at a pure shear or a simple shear sort of deformation. Okay? The ellipse is called strain ellipse. So this is what we will call as the strain ellipse, and describes the amount of elongation and shortening in any direction in a plane of the homogeneous deformation. A circle of unit radius and flattened vertically parallel to the coordinate axis is homogeneously deformed into an ellipse with 2 major axes, which initially were diameters of the circle. The strain ellipse is a 2-dimensional graphical concept to visualize the amount of linear or angular strain. Okay, so here this would be my angular strain, and in here, if I just calculate this is D and this is L. So L by D, of course, is my linear strain. Okay. The longest and the shortest radii of the principal strain axis, they are called principal strain axis, define the strain ellipse. So if I look at this strain ellipse, okay, these two axes A and B would be my principal strain axis. Okay. In the considered coordinate parallel shortening, the axis will be the vertical short and the horizontal is the long axis. So the length of you can actually show that the length of the long axis, the length of the long principal axis would be nothing but 1 plus epsilon 1, and the length of the short axis will be 1 plus epsilon 3. Okay, so what do I mean by that? Just I have a picture for that. Okay, so this is my initial circle, which is now converted to an ellipse, and I can actually calculate epsilon 1 and epsilon 3 in both directions, epsilon 1 and epsilon 3 in both directions. And then I can calculate, the major axis will be 1 plus epsilon 1, and the minor axis will be 1 plus epsilon 3. So epsilon 1 means we have defined epsilon 1. Epsilon is the elongation. So epsilon 1 is the elongation along x-axis, and epsilon 3 is the shortening actually along the y-axis. Okay. Now, the shape of the strain ellipse, okay, would define what sort of deformation we are looking at. Okay, the shape of the strain ellipse would determine what sort of deformation we are looking at. Okay. So now I'll try to explain this particular diagram to you. So in the x-axis, I am drawing 1 plus epsilon 1, and in the y-axis, I'm plotting 1 plus epsilon 3. Nothing but, so what does that mean? In the x-axis, I'm drawing I'm plotting the length of the major axis. In the y-axis, I'm plotting the length of the minor axis. Okay. Now, if and r is defined as 1 plus epsilon 1 by 1 plus epsilon 3. So r equals to 1 line will be defined by a line which is having a 45-degree slope in this particular xy plot. Okay, and you can see if r is equals to 1, that means epsilon, if r equals to 1, then 1 plus epsilon 1 is equals to 1 plus epsilon. So r is equals to 1 means, that will indicate that epsilon 1 and epsilon 3 is equal, right? Epsilon 1 and epsilon 3 is equal. So that means a circle gets reduced or enlarged to another circle. Okay, a circle gets reduced or enlarged to another circle. Okay, so this is the initial shape. Okay. So if the circle remains here, that means there is no change in shape. If the circle goes this way, that means that the initial length in both the direction has reduced. And if I go this way, then I will see that in both the direction, my length has increased. Okay. Now I define another three fields. Okay. So field one, where epsilon 1 is greater than 0 and epsilon 3 is also greater than 0. Okay. So what I am observing, that this is my initial shape of the circle. In both directions, I have essentially increment. In both direction, I have increment, but in the x direction, I have more increment. Now, this line defines epsilon 1 is greater than 0, but epsilon 3 is equals to 0. Okay, so that means there is elongation only in the x direction, but there is no elongation in the y direction. Now, field 2, where epsilon 1 is greater than 0 and epsilon 3 is less than 0, that means the x direction gets enlarged, but the y direction gets shortened. Okay. In this field, epsilon 1 is less than 0 and epsilon 3 is less than 0, is green field. That means in both directions, it has reduced. And in here, epsilon 1 remains 1, but epsilon 3, this is here, epsilon 1 remains 1, but epsilon 3 is reduced to, right, is less than 0. That means what has happened? That your x direction has remained the same, but the y direction has actually shrunk. Okay. So this is how you can, this is how based on the R value, you can actually place different sort of strains into perspective. Is that clear, everyone? It's very simple. If you do it by yourself, you will be able to understand it. Is this clear? Anyone has a question? Okay. And there is nothing to remember. You can draw it by yourself. Okay. So, as I was saying, the description of the strain ellipse can be done in two ways. One we call as the finite strain ellipse, that is the cumulative or the total deformation that I am looking at, point, sorry, I am looking at point A and then I am looking at point B. Okay, and I am not considering anything in between. Okay, so if I just define the cumulative and the total deformation, then that is what we call as the finite strain ellipse. And then there is another type of strain ellipse which are called infinitesimal or instantaneous strain ellipses. So that means between A to B, what I am interested in is many shapes, Maybe this becomes first like this, then it becomes bit more constricted, and finally it comes here. Okay. So I am interested in any of the instances. That is what we call as infinitesimal strain ellipse. Okay. This is finite strain ellipse if I am just considered at the final and the cumulative or the total deformation, and infinitesimal, that means I'm interested in any of the in between stages. Okay. We'll discuss about this later on. Now, there is something I want to introduce here. We will discuss about plane strain in greater details when we talk about three-dimensional strain. Okay. So plane strain means the strain, the deformation only happens only on one plane. And here I am going to discuss about I'm going to discuss about the experiment that I had just talked about. So what we did in that experiment, if you remember, that I had this block. Okay, think about this block that I want to deform. Okay, suppose I am putting a plate here. I'm putting another plate here. Okay, and I am squeezing it along this plate, and I am allowing this part to move, to deform, but I am kind of putting a lid at the top. Okay, I'm putting a lid at the top. I am not allowing the material to flow in the vertical direction. Okay, so what I am, in other words, what I am doing, that this is my plane, this is my body. Okay, and I am only allowing this XY plane to contain the deformation. I am stopping the Z direction. So I am putting some sort of limiting factor. I am putting some boundary conditions at the Z direction, and I am only allowing the deformation to happen on the XY plane. Okay, and such type of deformation is called plane strain deformation. Such type of deformation is called plane strain deformation, simply because the deformation is only restricted on a single plane. We are allowing the direction which is perpendicular to that plane to actually be fixed. Okay, and such deformation is called plane strain deformation. And plane strain deformation is further subdivided into two categories. One we call as pure shear, and pure shear is a coaxial deformation, and simple shear, which is, we call it a non-coaxial deformation. Now we will see why it is a coaxial deformation, this pure shear. Now, coaxial deformation means that, this is my initial circle, and then I have defined my x-axis and y-axis. And in all corresponding stages of the pure shear deformation, I hope you are understanding why it is pure shear deformation. So this means this is the plane that we are looking at is the XY plane. Right? This is the XY plane, and we have kept this Z direction is stopped. Okay, we are not allowing the material to flow along Z direction, and we can see that this, in each of these stages, the major axis and the minor axis are parallel to each other. So x dashed, x double prime, x triple prime, x 4, all of them are actually parallel to each other. Similarly, the y-axis are also parallel to each other. Okay, so these two mutually perpendicular axes, okay, where there is maximum elongation and where there is minimum, maximum shortening or minimum elongation, these two mutually perpendicular axes remain parallel to each other, remain actually parallel in each of these stages of deformation throughout the deformation. Okay? And such deformation is called coaxial deformation. Okay? So the principal strain axis remain parallel to the same material lines throughout straining. I hope you are understanding. That is the axis of the finite and infinitesimal. So this is my finite strain ellipse. This is my finite strain ellipse, and all the in between stages are my infinitesimal strain ellipses. Okay, so the that is the axis of the finite and the infinitesimal strain ellipses remain parallel throughout the deformation, and such deformation is called coaxial or irrotational deformation. Okay, such deformation is called uh, um, coaxial or irrotational deformation. So a constant volume coaxial. So how pure shear deformation is defined then? A constant volume coaxial plane strain deformation. Okay. I hope you understand now. It's a constant volume deformation. So the volume doesn't change. Coaxial means the principal axis of strain remains the same, and plane strain deformation means deformation is only restricted on a single plane. Okay, so that is how pure shear deformation is defined. So all the lines except the principal strain deflects towards the line of maximum extension, and we will see that now. So these are my displacement vectors. Now what we observe, that you know So this is my initial stage. This is my initial stage of the pure shear deformation. Pay very good attention, huh? And this is the final stage. This is the finite strain ellipse, okay? And in between, all of them are infinitesimal strain. So now this is my stage one. This green line is my stage one. Okay? Now observe this particular strain ellipse. Observe this strain ellipse. Okay. See this point P remains here. P. It's like a parallel translation. Okay. P dashed goes to P dashed. Okay. Now, say for example, this line is simply shortened. But what happens to a line which was here? What happens to that line which was here? That line, you would see that in here comes somewhere here. So there is a slight rotation. Okay. So except for these two lines, all the lines actually rotate. Okay. All the material lines actually rotate, and they rotate towards the maximum strain axis. Okay. So the material lines along the principal strain axis do not rotate but deform. There are two such lines and they are perpendicular to each other, be the major axis and the minor axis. Any other material line rotates and deforms. This line rotates in the stretching direction. There are two lines never deform but rotate towards the stretching directions. These lines have no finite longitudinal strain. Okay. So now let's discuss about non-coaxial deformation. Non-coaxial deformation means the axis of the finite and the infinitesimal strain ellipse are not parallel. Okay? Detailed observation reveal that the principal axis of strain ellipse rotate through different material lines at each infinitesimal strain increment. Non-axial deformation is rotational. Okay? So you can see here, this is my initial strain. This is my initial shape, and this is my first strain ellipse. This is the major axis. This is the minor axis. This is the second strain ellipse. This is the major axis, the minor axis. And of course, you can see that my major axis and the minor axis of the strain ellipse is actually rotating. Okay. So they are not, this is my finite strain ellipse. Okay. They are rotating. Okay? So this sort of deformation is called non-coaxial or rotational deformation. Okay. So how simple shear deformation is defined? It's a constant volume deformation again. It's a non-coaxial deformation, but it's a plane strain deformation. So what is the difference between pure shear and simple shear? What are the similarities in pure shear and simple shear? That both of them are constant volume and both of them are plane strain. But in one case, pure shear, it is a rotation and non-rotational deformation or coaxial deformation, and simple shear is a rotational deformation and non-coaxial deformation. Okay, so this is the difference between pure shear and simple shear. Okay, now I want to give you a assignment to do at home, and it's not something that you have to submit to me, but I will ask questions later on. You can read about it also in S.K. Ghosh's book or Ramsey's book anywhere, but you can try doing it yourself. Okay. What I want you to understand, what I want you to do is, suppose take the example of pure shear. Okay. And consider a line which has a length of L1. Consider a line which has a length AB, which has a length of L1. Okay. So I want you to plot how L1 will change with pure shear deformation. Okay. Also, if you subject the same block to simple shear deformation, how the length of this line L1 will change. Okay. So for simple shear, you can take a line AB here and a line AC here. Okay. So pure shear, you are simply squeezing it back, and simple shear, you are providing a shear. Okay. Remember this line AB or AC, that will not be parallel or perpendicular to the long axis and short axis. That is simple. So you have to take the length L1, which is the initial length, and show me how the length will change with pure shear deformation and how the length will change for simple shear deformation. Okay, I might ask anyone in the next class to show me how it goes. Okay, so you can prepare that a simple slide, yeah, for yourself, and show it to me in the next class. Okay, and we will discuss later on. If you have a question, it's the time to ask.
Sir, what we need to do with the line KC, sorry, AC.
Yeah, you have to tell me how the length of that line will change with deformation, both in case of pure shear and both in case of simple shear.
So that is for both the lines from A to C and A to B.
Yeah,
Okay,
for
sir.
both of them. Yeah, how the length will change, whether the length will remain constant or the length will change. If it changes, how will it change? Whether it will be extended, whether it will be shortened, or whether it will be first extended then shortened, or what will happen? That is something I want to understand. Okay, in both case of for pure shear and simple shear deformation. So if you do that exercise, the concept of pure shear and simple shear deformation will be very clear to you. Hence I am asking you to do that exercise by yourself. Okay, any other question? You can start reading the book of SK Ghosh. It's available in the library as well as it's available online. You can find it out. Yeah, it has a chapter of strain. That is what we are studying now. Any question? Right? If not, then I will stop the meeting here and I will see you on Wednesday for the lab class. Those who are here, and then Thursday for the lecture again. Thank you. Okay. Just before I leave, before you leave, I hope Srivats, you are here. You can email to everyone because you are here. So those who are coming to the lab, okay, I want you to bring these things with you. Okay, I'll just write it down here. Please bring these things with you. Okay, one is of course printed marionette, both equal area and equal angle. Okay, A4 size. Then pencil. I want to see everyone having these things. Okay. Art, board, board, pin, flat, bottom. Then you can buy one of you, each of you can buy a box of board pin. Okay, hardboard, pencil. Then you need to have protractors or diagonal scale. Have I done protractors or diagonal scale? If you have a protractor, then another scale. If you have a diagonal scale, you don't need a separate scale. Okay, and lab notebook. So these are the things you must bring with you. Sivats, as you are here, can you please email to all the students who are here to bring these things on Wednesday? Yeah.
Yes, sir.
Okay. So these are the things. I hope you all know because you have all done the lab class before, so it's very similar. So we need all these things to do the stereo net exercise, of course. Yeah, and then I will see you on Wednesday. Thank you.